Well, good morning, everybody. Thank you for joining Flex Train, a flexible training opportunity brought to you by Johnstone Supply. So I wanted to spend a little bit of time this morning talking about inverter technology and how things are changing in our industry. Because we look at the development of particularly our metering devices. We did a couple classes on metering devices talking about how we've moved from, capillary tubes into fixed orifice pistons and then into thermostatic expansion valves and automatic expansion valves. And we're now really moving into electronic expansion valve technology. So with any metering device, we're really doing one thing. We're controlling the flow of refrigerant through the evaporator coil, and we're trying to maintain maximum efficiency across that indoor unit, right? Well, with the electronic expansion valve, we're still doing the same thing as a regular expansion valve. We're just now going to do it with digital sensors. If we look at an expansion valve, a standard expansion valve, thermostatic expansion valve, we use a sensing bulb that has a capillary tube tied back to the head of the valve that has the same refrigerant in that head and in that capillary as what is in the system. So on an R410A HVAC system, we have R410A refrigerant inside of that sensing bulb. So as we start getting excess liquid refrigerant in our evaporator coil, we see that temperature getting very low. So it changes the pressure on the bulb. So as the temperature goes down, so does the pressure inside of that bulb, which in return changes the pressure on the diaphragm at the TXV. And so it starts pinching down and slowing down the flow of refrigerant, and vice versa. When the temperature goes up on the sensing bulb, the pressure goes up. So as the superheat goes up, it senses that change of temperature. And so then it modulates the valve by, changing the pressure on the head to let more refrigerant through. So with an electronic expansion valve, we're really doing the exact same thing, but we're going to do it with some digital sensors. And I just put this presentation together a couple of weeks ago for our Daikin FIT equipment, because that is really our most popular inverter right now. If those of you who are not familiar with the Daikin FIT, it's rated at a 17 SEER inverter that uses a mini split style outdoor unit, but then it connects to a standard electronic expansion valve air handler or cased coil when it's matched up to a gas furnace on the indoor unit. So they have them in AC and heat pumps. So with that electronic expansion valve, we're now going to modulate that outdoor unit, because that outdoor unit can vary its speed, its RPMs, from 35% up to 100%. And I can actually overdrive it by an additional 15% if needed in boost mode. But typically it's between 35 and 100%. Well, it has to know what the load is, what the demand is on that indoor system. So what we do is we add a pressure transducer and we add a temperature sensor or two. Daikin FIT, it uses two temperature sensors, one on the outlet of the metering device, the outlet of the EEV, and then one on the outlet on the suction line, outlet of the coil. And then it uses that pressure transducer. So it's reading true superheat of the coil, so that when our heat load changes on the coil, so say we open up the front door and a large inrush of heat comes into our structure, well, we have all that excess heat going across the evaporator coil now. So what happens? Our superheat increases because we have excess heat on the coil. So it reads that increase of heat load on the coil by using the temperature sensors and the pressure transducer. And so then it now sees that it needs to change its capacity. It needs to increase the capacity of the outdoor unit. So it starts ramping up the outdoor unit to compensate for that. And consequently, it will end up ramping up the blower as well. But it all starts at that electronic expansion valve. So if we look at that, it's got its own power supply. So most manufacturers follow a principle like this. Remember when we were talking about ECM motors, there's really only two types of ECM motors: an ECM constant speed and an ECM constant airflow. Yeah, Katie, almost to the next slide. I'm still on this first one. I'll be moving there in just a second. So with an ECM constant torque, we are pre-programming that module for a couple ramp profiles, usually 3 or 4 speeds, right? So it has all of those profiles pre-programmed into the module that's on the back of the motor. If we talk about an ECM variable speed, well, now we're actually going to start using inputs, temperature sensors and pressure transducers. We're going to give inputs for our module so that it has a live reactant. It's not just pre-programmed, it has live response. Well, we have that same technology in inverters as well. So if we look at a multi-speed inverter, say particularly like the Bosch or a lot of the Green Speed are that way, they will do a pre-programmed ramping profiles for that ECM motor. Because remember, all that we did when we went to an inverter compressor is we took out the permanent split capacitor motor and we put in a true ECM motor. Same housing, we just swapped motors. So we're just getting a more efficient motor out of it, but we can have either an ECM constant torque with pre-programmed profiles or an ECM variable speed. So it depends on the actual manufacturer of equipment. All of our Daikin inverters are going to be those true ECM variable speeds. So they're going to use inputs to dictate what we're doing outside. So if we look at this particular wiring diagram here, I'm going to grab my highlighter. So here on the right hand side, this board is the actual, actually it'd be that board, is the actual layout of the control board that is on that electronic expansion valve air handler. This happens to be the cased coil version. So if we look at it, on that control board, coming from our air handler or gas furnace, we are going to add an additional transformer. So they send a transformer with that so we can supply an additional power source for this control board. So at our indoor unit, we're going to install a new transformer, and it is there only to feed 24 volts to TR1 and TR2 or TH2. So that is our 24 volt power supply that feeds this entire coil or control board. And off from that control board, we're going to have some inputs. So this is the actual sensors that are on our coil. We're going to have our pressure. It says pressure sensor. It's a true transducer. We're going to have a couple temperature sensors, and then we're going to have the actual solenoid of the EEV. And then from the furnace or air handler, we're going to supply an additional signal, which is the actual operating signals. So it's going to be, for our Daikin, we're going to use blue and red to feed 24 volt AC over to the board, and we're going to use number 1 and number 2 for communicating. So all of our communicating signals are really just happening on number 1 and number 2. And we'll talk about that here in just a second, what we're actually doing with those. It's pretty simple technology. So if let's move down here real quick. So we know that our control board is dictating the RPMs and the RPSs of the outdoor unit. So if we look at how those are going to be wired, if we take a full wiring diagram for our entire system, we are going to say we're going to be at our indoor unit. So this particular one, we're actually using the Honeywell CTK04 thermostat. So we're going to have C at our thermostat and R at our thermostat, because that's just going to feed that nice big digital screen. We're going to have all of that power starting at our furnace or air handler, right? That's where our main transformer is at. So it's going to feed 24 volts to feed our nice big screen, and we're going to feed that 24 volt signal over to our cased coil or air handler, whichever one we're using. And we don't need it to the outdoor unit, because remember, with our inverter outdoor units, we already have a power source on that board. The boards stay energized 24/7 on these inverter outdoor units. So we don't need a R and C to feed the outdoor unit. We just simply need to have our communication. So when it comes to communicating, we're going to use an entire mesh network. So we're going to communicate on number 1 and number 2. So we're pretty much going to be starting at our furnace and our air handler. We're going to be tying it to number 1 and number 2 at our thermostat. We're going to tie it to number 1 and number 2 at our coil, and we're going to tie it to number 1 and number 2 of our outdoor unit. And that's really all the communicating network is going to do. So for Daikin, they call it the Comfort Net system. But if anyone is familiar with 5-volt DC communicating networks, it really all goes way back to Climate Talk. So Climate Talk was a communicating platform. Is actually introduced by Emerson long time ago, probably 20 years ago. I don't even know exactly how long it's been out. I use Climate Talk a lot in our commercial industrial communicating equipment. All the CPC products, we're using a 5-volt DC signal. So what we're really doing is we're using a positive and a negative DC signal, and it's communicating back and forth all of its commands. And it's very simple to understand what it's doing from a troubleshooting aspect. So if we look at that one that I put together, that little slide for troubleshooting, what it's telling us is that if we're looking at number 1 and number 2, they're very polarity sensitive. So we have to have all the number 1s connected to number 1s and all the number 2s connected to number 2s. Because what we're doing is we're taking that 5-volt DC signal and we're going to break it up into a positive signal and a negative signal. So if you take your meter and you're testing communicating networks that are using 5-volt DC, you can put your ground terminal, your negative or black terminal, whichever you're designating it as, on ground or common, because common should be grounded. Common side of our transformer should be grounded. Go from common to number 1, and you're actually going to see a positive DC signal. And it's typically going to be like 2.5 to 3, somewhere in that ballpark. It's about half of that 5-volt DC signal. So then if we go from ground or common to number 2, we're actually going to see the inverse of that. We're going to see a negative DC signal because it's sending out on number 1 and it's coming back on number 2. So we're going to have polarity difference on those. So what we look for is we actually have a differential between those. It's called a bias. It's called a DC voltage bias. So if I go from ground to number 1 and say I've got, in this example, 2.8 volts DC. And then I go from ground to number 2 and I have a negative 2.2 volts DC. Well, I subtract the 2 of those and I've got a 0.6 difference, right? That is my bias. So what I'm looking for is a 0.6 volts DC bias or greater. If I have less than 0.6 volts DC, my system can't communicate properly. So say I've got a bad connection in a wire nut. Maybe I've got some moisture inside of a wire nut. Or say I've had a conductor where I've had a mouse chew on the insulation and chew through the insulation. You know, that conductor was good at moving electrons through it until it gets oxidized. Right? So if we get a critter that gets into the control wire, chews through the insulation, and now we have contaminants that gets onto our what used to be a nice shiny copper conductor, that conductor is going to oxidize and it's now not going to flow electrons properly. So when we're talking about 5 volts DC and sometimes in milliamp of current, we're talking low voltage and low current. So it's super, super critical to have proper landing on those number 1 and those number 2 terminals, because it has to be able to talk and it has to have a differential voltage of 0.6 volts or higher. So on our equipment, on our Daikin equipment, they actually install a separate terminal called the DS1 switch, the DS1 bus, and it actually helps change the bias. So say I've got an issue where I can't change my control wire. I have to reuse that 18-2 solid thermostat wire that was already running in my outdoor unit. Well, as long as I'm getting 0.6 volts DC bias or above, the system's going to work properly. If it gets below 0.6, I can actually turn on that bias and it's going to boost the differential between the 2 of them. So it's going to help change that differential so it can get to that 0.6 volts. But it's really critical to understand that on that Climate Talk, on that Comfort Net communicating system, if we don't have a 0.6 volt DC bias between the 2 of them, it's not going to communicate properly. So most of the problems that we run into with inverter technology and communicating technology is in the control wires. So it's just a matter of understanding how those things communicate. So we've changed our motors a little bit as well. So, you know, if we're now going to use an ECM motor in our vapor pump, our compressor, doesn't it make sense that we're just going to use an ECM motor for our condenser fan motor as well? So that's what we're going to do. So we're going to remove the permanent split capacitor motor for the condenser, and we're going to replace it with an ECM. And we're going to be a true variable, so all of our signals are going to come directly from the control board. So the only thing from the control board to that condenser fan motor is 3 wires. That's your 3 phases, A, B, and C. So on diagnosing these motors, it's very simple. All we're going to do is make sure that we have the same resistance between all three of our windings. Because remember, an ECM motor, if you remember from our ECM classes, an ECM motor, the actual motor itself, is just a plain old three-phase motor. So it's a very well designed but very simple product. So if we're going to test these things, we're just going to check, make sure that we have our voltage, and it's not going to be exactly 120 or 240 like we used to know. Because we're going to have, a change in voltages and controls. We're doing it now by hertz, by frequencies, to change the speeds, not by changing our voltages. So we just simply check those on our particular chassis. On our Daikin FITs, we really only make 2 chassis. So from 1.5 up to 3 ton, the actual chassis is all the same. It uses the same condenser fan motor. It just uses a different capacity compressor, really, because even the control boards are the same. And then from our 3.5 to a 5, it's a different chassis, but it's got a little bit larger condenser fan motor. So we can take our meters and we can ohm between pin number 1 and pin number 2. And if it's on the smaller chassis, it'll be between 15 and 21 ohms. If it's on a larger chassis, it'll be between 10 and 15. And then I'm gonna go between 1 and 3 and 2 and 3. And those should all be the same, right? Because it's a 3-phase motor, they should have the same windings to them. So very simple design in our inverter technology. If we look at our compressor, same thing. Our compressor, remember, all compressors are a vapor pump being driven by some type of locomotive force. So in our residential and unitary HVAC products, we're using a vapor pump that is being driven by a motor. So we just took out that permanent split capacitor motor and put in a 3-phase motor. It's as simple as that. So instead of seeing those C, R, and S terminals on your permanent split capacitor compressor, we're just going to have U, V, and W. That's our 3 phases. And the same way with those. We can test those between each terminal just like on those condenser fan motors, and we're going to have the same resistance between those. And then we can check, of course, to ground. We're always going to mega ohm the insulation on our motors. So we're going to mega ohm the insulation going to ground on our compressors, just the same. So that's all we're going to do. Now, when we start talking about the sensors and the temperature or pressure transducers that are going into these pieces of equipment, we just need to understand what they are. It'll help you see what's going on inside of an inverter. Remember, this is built for our Daikin equipment, but it's really good for all inverter technology. It doesn't even matter the size of the piece of equipment. It's using the same principles. So if we look at that says pressure sensor, but it's truly a pressure transducer. We've all used or seen at least a rheostat, right? A dimmer control for lights or for fans. Well, all we're talking about is it's a potentiometer. It's a variable resistor. So as it moves, it's going to change its resistance. Well, inside all pressure transducers, we're doing the exact same thing. We're just taking a pressure and applying a pressure onto something that we're going to move. And as we move it, we actually change its resistance. And that's all a pressure sensor is. It's just a potentiometer. So what we do, we still talk on that same 5 volts DC. So we're going to, we've got a transformer that's providing 5 volts DC for our communicating network, or we're simply just going to use that 5 volts DC that our generator had already produced, and we're going to use it to go through all of our temperature sensors and our pressure transducers. And we're just going to look for a change in voltage, a change in our potentiometer. So when we look at those pressure sensors, let me grab my Sharpie again here and let's take a look at that. So all I'm going to do, because it's just a 3-pin, it's a 4-pin connector, but we're only using 3 pins of it. So we are going to have a dedicated ground, which we're going to use as the black, the pin number 3. We are going to have a dedicated 5 volt DC signal coming in on number 4, and what comes out of our potentiometer comes out on number 1, and it's just a variable 5 volt DC signal. So for any brand, you can check those pressure transducers if you think that you're having an issue with one, simply by measuring the voltage that's coming out of them, or by unplugging it and checking the resistance that comes across it. It's really simple technology when you look at it from that perspective, because even our actual temperature sensors, they're just changing the resistance so that we can change the voltage. So when we look at our expansion valves, what are we doing with an expansion valve? People always wonder, hey, what is that power head actually doing on that electronic expansion valve? It is the simplest thing if we look at the design of it. If we look at the power head on an electronic expansion valve, it is simply 4 solenoids all into one head. So if you've ever looked at the design of it, I need to do probably a class just on EEVs. All an EEV is inside is a tapered cone and a piston that is also tapered. So as that refrigerant is flowing around that piston, it has to go through that tapered seat. And it's going to do that by how much space is in between the piston and the seat. So we can step that piston up and down simply by using some magnetic coils. So if we look at that head, it really is that solenoid that's on top of that electronic expansion valve. It is just 4 coils. And each one of those will have the same resistance to each other. All of our Daikin, and this is going to be almost all Daikin pieces of equipment that has an EEV, whether it's a unitary, it's a commercial, whether it's a mini split, same principle. We are going to have 4 coils inside of that one little head. And if you've ever installed any type of electronic expansion valve, when you first power them up, you're going to hear it. And all it's doing is it's firing those in order. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And it's trying to move that piston all the way open so that it sees where its maximum open point is, and then it's going to go 4, 2, 3, 2, 1, 4, 2, 3, 2, 1, 4, 2, 3, 2, 1, and it's going to get it until it stops and meets a little bit of resistance, and it goes, oh, well, this is closed. So it's looking for open and it's looking for closed. So when we see those, and if it says that it's got 250 steps, all it's doing is 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, and it's trying to open itself all the way up, and then it'll close itself all the way down. So we can check the resistance on those solenoids, because a lot of people will condemn an electronic expansion valve in the field without ever even checking the solenoid. And so the solenoid is just 4 coils, all going back to common. So like ours, it's on a 6-pin connector. Well, here's our 6-pin connector right here. And we're only using 5 of the wires. And we make sure that we put common out there on its own so that everyone knows that, it is common and it's away from the rest of the wires. So we leave a blank one in between them. So there's common. So we're simply going to check from common to coil number 4, common to coil number 3, common to coil number 2, and common to coil number 1. And all 4 of those should be identical. You should have the exact same resistance between each one of those. And if one of them is wrong, is off than the others, then we can't complete our sequence. Our 1, 2, 3, 4, 1, 2, 3. We can't complete that. So we just simply check the power head to see if our power head is actually good. And that will tell us, a lot about the operating of the system. Because if I check all 4 of those and one of them is bad, there's no reason to dive into the refrigerant side of the system. I'm just simply going to go get a new power head, replace the power head, and see if that has now solved my issue. So most of the times we find in the field, the electronic expansion valves themselves really don't go bad. The only way an electronic expansion valve will physically go bad inside is if I get a bunch of contaminants in my system. If I didn't flow nitrogen while I was brazing, and if I didn't draw a proper vacuum to get moisture out of the system. That's the only thing that'll cause them to go bad. They're so simple by design. So most of the time, what actually fails is that electronic expansion valve power head. So most of them you're going to find are going to be between 40 and 50 ohms. All of ours are between 40 and 50 ohms. So we're going to ohm out all 4 of our windings, and we're going to see what those look like. Now, if I go into our thermistors, we were talking about the thermistors being the same thing. It's just a change in resistance, right? That's all temperature thermistors do, is they change resistance when they change temperature. So we can do the same thing. We can see what voltage is coming through our thermistors, because we're going to use that 5-volt DC again. Our generator's producing it. Why not use it for all of our controls? So we have to change our mentality. If we were talking about, standard in a HVAC low voltage wiring on unitary systems, on legacy wiring, it's all 24 volt AC. We run that through all of our sensors. Well, when we get into inverters, we're just going to use that 5 volt DC to run through everything, all of our temperature sensors and pressure transducers. So our temperature sensors are just going to change resistance based on their temperature. So I'm going to send in the exact same principle. I'm going to go into, let me grab my Sharpie again. So if I have a temperature sensor, it's literally just a resistor. It's all that it is that can change its potential. So I'm going to come in with 5 volts DC, and depending on the resistance of my resistor, whatever voltage comes out is going to be a relationship to my pressure. So I can measure that while this thing is running. I can look at my chart, and my chart will tell me exactly what that is. So if I look at this chart and I said, hey, I've got 95 degrees outside, I can either unplug my sensor, and I should have around 13.7 k ohms of resistance, or if I check the DC voltage coming out of that, it's going to be about 1.42 volts DC. Super, super, super easy to read and understand these things. And when we think about, it's all operating on this 5 volt DC signal. Well, what happens if we have a problem in our communicating network? What if the homeowner is up in the attic and he's doing some kind of work and he chops the control wire in pieces? What if a critter gets into the control wire? What if the thermostat goes bad? What if the kid's running down the hallway with the baseball bat and it knocks the thermostat and has crashed this $400 thermostat, and it's Saturday night and you can't get one? Well, if it all runs on temperature sensors and pressure transducers, what is it really using a thermostat for anyhow? The only thing it's doing is just saying, hey, this is where we should or should not be running, right? So we could simply lock these things into emergency mode if we need to. If we have some kind of a communication issue from our thermostat to our indoor unit, bad thermostat, whatever, we can actually put these into an emergency mode so it will just run on its own. It will just use those temperature sensors and pressure transducers to modulate the temperature on the coil. And so we can put those in a locked-in capacity. So we can go to our dip switches on our particular brand, on our Daikin stuff. It's on DS2. We can go to DS2 and we can lock it into 30% emergency run. We can lock it into 50% emergency run, or we can lock it into 70% emergency run. So it's just a matter of locking it into place. So the next issue that we talk about when we're looking at inverter technology, as we're moving into this, we already have temperature sensor and pressure transducers on that evaporator coil, right? Well, do we even need a thermostat at that point? Because all a thermostat is our potentiometer. It's just telling us what the room temperature is, right? It's just a temperature sensor. So as we start moving into this inverter technology, the thing that we have to be aware of is that it is just a matter of manipulating voltages that is going through these temperature sensors. If we have a preset temperature or a preset humidity, if we even wanted to, we can keep that in our piece of equipment. As long as there is air moving across our evaporator coil, we can control the entire environment. So as this technology moves forward, don't be surprised to start seeing pieces of inverter equipment that doesn't even require the use of a thermostat. All it needs to know is what temperature are we the most happy. And in today's world, that's literally a matter of tying my piece of equipment onto my Wi-Fi network, and then I can just use my phone or a mobile device to tell the system what the temperature should be, right? So we're going to start seeing a lot of changes in the way we understand HVAC, and it very much has to do with our equipment using digital inputs to control digital outputs, and everything is going to be based on that same communicating principle. Most manufacturers use a 5 volt DC signal. So when we talk about all the different brands of communicating equipment, what most manufacturers will not tell you is that they're all using climate talk. They're all manufacturing their principles on climate talk. The only reason communicating equipment doesn't talk between manufacturers is for firewalls that they put in their own software, because the actual principle is the same. And most companies will not tell you that, but from field experience, climate talk is the communicating 5-volt DC signal that you're going to run into all over the place, even in the commercial industrial side. So it's very interesting when you start seeing that in different manufacturers and different brands, and to find out that no matter what they call their own technology, it's pretty much all the same. It's all doing the exact same function. So not a lot this morning. I've got a site visit here in a little bit, so I couldn't run too long this morning, but I wanted to brush on inverter technology and electronic expansion valves and how they work together. And I'm going to open up the lines. If anybody has any questions or any kind of comments that they'd like to discuss on inverter technology, now's a good time. Okay, well, I think I'll wrap it up, everybody. Have a happy 4th of July. Hopefully everybody gets to take off tomorrow and have a long weekend. For those of you like myself that are on call, phooey, try not to run too many calls. So everybody have a safe and happy 4th of July. I'll see you all next week.